Welcome to the last session of the day, which I believe is called Cryptanalysis 3, or something of that sort. Symmetric Cryptanalysis 3. We have 3 very interesting talks today, and it would be good if we have the, yes, excellent, thank you. First one is proof of mirror theory for a wide range of Z-max, and it will be given by Abhishankar Saha, joint work with Benoit Cogliani, Avijit Duttu, Mridul Nandi, and Jacques Patarin, and the talk will be given by Abhishankar.
Hi, everybody. I'm going to present proof of mirror theory for a wide range of Z-max with a joint work with Benoit Cogliani, Avijit Duttu, Mridul Nandi, and Jacques Patarin. So, mirror theory is born out of Patarin's age coefficient technique, which I will briefly introduce first and then go into mirror theory. So, in the indistinguishability setup, the adversary interacts with the construction in the real world and with its idealized counterpart in the ideal world. And the advantage of the adversary is bounded by the statistical distance between these two random variables, tau RE and tau ID, which is basically representing the transcripts generated in the respective worlds. So, for a subset of good transcripts, which we define, age coefficient technique basically bounds the statistical distance by this value, where the ideal world probabilities, this one and this one, are easy to calculate because it just involves a random oracle. However, this real world probability is, to calculate it, it is much more involved. So we need a lower bound on the number of transcripts that are both real world realizable and also good to get this upper bound on the statistical distance. Now, this real world realizability restrictions and goodness restrictions, they are manifested in terms of system of equations, and we need to lower bound the number of solutions to the system of equations where mirror theory comes in. So take, for example, the Zork construction. So it has as input xi and as output this entire y vector, yi vector, and the underlying primitive is a random permutation pi. So as one can see, if this is the transcript tau, so if for any yi, one component of yij is equals to 0, or if two components of yi are equal, then the adversary obviously understands that it is interacting with the ideal world, because in real world it will never happen. So we define our good transcripts to be those transcripts for which such trivial attacks doesn't work. And now, if we represent the outputs of the random permutation by capital Xij's, then we get this real world realizability restrictions, which you can see is a system of bivariate equations and non-equations, where the non-equations just mean that the variables are pairwise distinct. Okay, so now we go into mirror theory. So given a system of bivariate affine equations, we can always equivalently represent it with a labeled undirected graph, where there is an edge between two variables. So the vertices are the variables, and there's an edge between two variables. If there is an equation between those two variables, the label of that edge being equal to the coefficient of the equation. Okay. So now you can see that for this system of equations to have any solution, any cycle in this graph must have label sum equals to 0. Also, if the solution needs to be pairwise distinct, any path should have label sum not equals to 0. Okay, and if you if you assign value to any variable, any vertex, all the other vertices in its component gets determined. So that is how components become a significant factor in our analysis. And in fact, Z-max in the title of our paper is the size of the largest component. Also, we can transform any system of equations into an equivalent system of equations which has the exact same set of solutions, however, which has as components stars. Okay. So how do we do that? As we choose a center of the star, say x1, and then just for any other vertex in its component, we introduce an edge between x1 and that vertex, and as label of that edge, we give the label sum of the path between x1 to that vertex in the original graph. So and all other edges become redundant, all other equations become redundant. So we get a star component like this. Okay. And this is called the standard form of the system. Now, in the labels of the edges of the star cannot be equal because, of course, then, so suppose if these two values are equal, then these two vertices would get the same value. That is not permissible, pairwise distinctness. Again, this value cannot be 0 because then this value and this value will be equal. So these things defined here, gamma 1 to gamma q, must be sets. And now we have shown that how a system of consistent system of equations can be represented by a set system containing as many sets as there are components, with each set having size same as the size of the corresponding component. We fancifully call it a galaxy of stars. So how to generate a solution to this system? So we first can uniformly and independently generate q n-bit values, assign them to the centers of the stars, and automatically the other vertices get determined. So this is our generated solution. And if we take any particular pairwise distinct solution to the system of equations, then our generated solution will be same as that particular solution with this probability, because just the centers have to match. So this is 2 to the minus nq. Now we define a disjointness event where the translates of these sets gamma I by Ri has to be disjoint, which is same as saying that this R tuple gives a pairwise distinct solution for this system. And P gamma, the probability of this disjointness event by our previous argument, is just the number of PD solutions to the system by 2 to the power of nq. Now you're ready to state our main result. So if the size of the largest component is of the order of 2 to the power of n by 4, and if the number of variables is has this order of 2 to the power of n bound, then P gamma is lower bounded by this value. So 2 to the power of n Pauling factorial v by 2 to the power of nv, which by our previous argument implies that the number of PD solutions to a system of equations having E equations in V variables has this lower bound, 2 to the power of n Pauling factorial v by 2 to the n to the power E, because E is V minus Q, because E is the number of edges of a forest of V vertices and Q components. And this bound actually has this intuition that if we have picked all the variables randomly, then each equation would hold with probability 1 by 2 to the power of n, and the number of pairwise distinct vectors of size v is 2 to the power of n Pauling factorial v. Okay. So we go into the proof strategy. So if there was just one star, and for any value assigned to the center, since gamma 1 is a set, all the solution that is generated by this R1 will be pairwise distinct, has to be. So P gamma is equals to 1 here. So for smaller galaxies, calculation of P gamma is very easy. So what we want to do is we take a big galaxy and we try to remove the stars from the galaxy. So say gamma 1 is S, the star we're going to remove. Then this smaller galaxy, so the number of the R tuples that will generate PD solutions for the smaller galaxy will not generate PD solutions for the larger galaxy if some of these S elements coincide with some of these gamma minus S elements. And the probability of such coincidence is just 1 by 2 to the power of n. That is how we get our crude bound. However, this is far from being done, because when we iterate this crude bound, which means that we remove stars 1 by 1 from the galaxy, we get a birthday bound on Q, which is not desired at all. However, if the total number of variables was actually under birthday bound, then this crude bound can be manipulated to get this bound on P gamma, which is mentioned in our main result. Okay, so we look further. Instead of removing a star, we just remove a link from a star. So this is our original galaxy. Suppose we remove this star and get this reduced, this link and get this reduced galaxy. And again, by the same kind of arguments. So an R tuple solving this reduced galaxy will not give a PD solution for the original galaxy if something like this happens, right? So, and this galaxy, which also and this equality happens with probability 1 by 2 to the power of n, and this galaxy, such that this equality holds, is actually this merged galaxy, where we have removed this component entirely and merged it with the reduced, merged a delta translate of it to the reduced star this, where delta is this, just algebra, okay. So, yeah, so, and also this delta translate needs to be disjoint from this reduced star, because otherwise the system will not have a pairwise distinct solution. Okay. So what we have the link deletion equation, which is very crucial for our paper. So which basically says that the R tuples solving the original, giving a PD solution for the original galaxy are basically the R tuples giving a pairwise distinct solution for this reduced galaxy with this X link removed, minus the R tuples that give a pairwise distinct solution for this merged galaxy. So we have expressed P gamma in terms of smaller galaxies, where here one link is at least removed, and here, although there is a large component, number of components is one less. And this summation this index set is basically contains all the delta and S dashes, such that the delta translates of S dash doesn't coincide with our reduced star S minus X. Okay, so what we want to do is actually, we want to express P gamma in terms of P gamma minus X. So we want this entire right-hand side to be in terms of this. For that, we need to express the merged galaxy probability in terms of the reduced galaxy probability and bound I. So we bounded I like this, where we have used two crucial points, that the group we are working on, the n-bit values with bitwise XOR, is of exponent 2, and the link that is being removed, this X has to be appropriately chosen, details in paper. So now, to express this in terms of this, we just denote them by tau and tau dash, write down the link deletion equations for these galaxies, and subtract them, take modulus, take maximum, and we get a recursive inequality in D terms, where D is the maximum possible distance between galaxies and galaxies where two of the components are merged. Okay, so technical things. So we get a nice recursive inequality for D terms, which is nice because this term will vanish after L-1 iterations. This term, though being under a summation, is multiplied by chi max by 2 to the power of n, which will be geometrically reduced. And the last ugly-looking parasite term will not be an issue after logarithm number of iterations. So basically, iterate this recursive inequality chi max dot n times, and then applying our crude bound, we get a bound on dq s minus 2. Why dq s minus 2? Because when we expand it, we basically get a relation between this merged galaxy and the reduced galaxy, and putting this bound in the original link deletion equation, we just get this. So for appropriately chosen X, P gamma is this times P gamma minus X. So obviously the next step is we remove links one by one until we have a galaxy of the size but the bound. And that is how, by simple algebra, we get our result. So this is, we have arrived at our result. And now this is the interesting part, how we apply our result for the security analysis of many constructions. One interesting one is 6-round Feistel. So to get the real-world realizability of this transcript tau, here we have to find the number of 6 tuples of functions f1 to f6, such that the Feistel of f1 to f6 of LIRI is equals to SITI for all I. So exactly corroborates with tau. So we have to calculate the number of 6 tuples. How we do it? We first generate the values of f1 RI and f6 TI, f6 SI, sorry. And then we modify our transcript. So now we have to just calculate the number of 4 tuples of functions f2 to f5, such that it exactly corroborates with this modified transcript tau dash. Okay. Now we come to the system of equations. So if we can see that if xi equals to xj, then f2 xi equals to f2 xj, and so ri zor yi should be equals to rj zor yj. So we get this kind of equations. But this xi equals to xj and ai equals to aj are determined by the random values we have determined here. So we know the equalities already. However, for z and y, we don't know whether they will be equal or not. So we instantiate what you call a framework. All this is not necessary, but what we see here, whenever we, so a framework is a collection of equalities on y and z variables. Whenever we instantiate that framework, we obviously instantiate also non-equalities among the other y's and z variables. So this is a system of equations and non-equations. And the number of such 4 tuples is basically this. Okay? So number of yq satisfying C1. C1 is this. Number of zq satisfying C2. So this is where the mirror theory results come in play. And when we put it there, and then also it has to be a good framework. What do you mean by good framework? So good framework is those frameworks for which this system of equations are consistent and has a pairwise distinct solution. So there are, and yeah, so we do the good framework thing. And we get such a bound on the number of 4 tuples. And doing H coefficient technique, we basically get this. And so we have that 6LR is n-bit SPRP secure from our mirror theory result. Okay? And now I'm going to end with some open variants of mirror theory, which are still to be proven. So as you have seen, our system of non-equations is basically xi's or xj is not equals to 0 to the power of n. So all the non-equations have labeled coefficient 0 to the power of n. So homogeneous system of non-equations. We can extend it to non-homogeneous system of non-equations, which becomes useful when the round functions, say, when the round functions of the Feistel construction are permutations. So then you need non-homogeneous system of non-equations. We can expand to groups of exponent not equals to 2, used in format preserving inscription. So also our Gimax has a bound of 2 to the power of n by 4 by root over n. We can expand it to any Gimax larger than that. And also our equations are all bivariate. So why not a system of, any system of equations? Yeah, so thank you.
Thank you for this interesting presentation. It was clear, so I don't have any questions, but perhaps the audience would like to ask a question? Then if not, let's thank the speaker again. So the next talk is non-adaptive universal one-way hash functions from arbitrary one-way functions, given by Xinyu Mao, and it's a joint work with Noah Mazur and Jipeng Zhang. So,
okay.
Please.
Thanks for the introduction. Hi, I am Xinyu Mao from University of Southern California. I will talk about non-adaptive universal one-way hash functions from arbitrary one-way functions. This is joint work with Noah Mazur and Jipeng Zhang. So let me introduce our main characters first. The first one is one-way function, which is well known. We say a function f is a one-way function if it is easy to compute and hard to invert given a random image. So the existence of a one-way function is universally accepted as a minimum assumption for cryptography. And our second main character is universal one-way hash functions, which is proposed by Noah Yang in 1989. So a universal one hash function, or WOOF, also known as target collision resistant hash function, is a keyed hash family, here denoted by C sub Z, with the following two properties. First one, it is shrinking, meaning the output length should be shorter than the input length. And we also want it to be to satisfy target collision resistance, meaning for any efficient adversary A, if A first commit on some target X, and then given a uniform key Z, it should be hard to find another collision X prime which collides with X under CZ. So Noah Yang showed that one-way function plus WOOF gives rise to digital signature. So this shows that although WOOF is a relaxation of collision-resistant one-way collision-resistant function, it still preserves some usefulness. And later, Rampo showed that WOOFs can be based on one-way functions. So combined together, digital signature can be built from solely one-way functions. So another useful fact is that universal one-way hash function can be easily constructed from an unkeyed function f that is shrinking and collision resistant on random inputs. This means given random input x, it should be hard to find collision x such that x prime, such that fx equals to fx prime. So from such an f, it is easy to build a WOOF. So let czx equal to f, z x or this is bit x or x. So we have if f is collision resistant on random inputs, then this cz defined in this way is a WOOF. So it is natural to ask about the efficiency of the construction of WOOF from one-way functions. So there are three major efficiency measures. The first one is the key length kn, where n is the input length of the one-way function. And the second one is number of calls to the underlying one-way function. And the third one is adaptivity, meaning that whether the invocation of one-way function are dependent of the output of previous calls to the one-way function. So if the calls to the one-way function are made parallel, we say this construction is non-adaptive. So our first result is non-adaptive construction of WOOF from arbitrary one-way functions. And compared to previous constructions, our construction made fewer number of calls, although at the cost of longer seed. We mentioned that this is the first non-adaptive construction. As a result, it can be implemented in NC1 with F oracle gates. And combined with a famous result, AIK06, assuming the one-way function f is computable in NC1, we can compile our universal one hash function to NC0. So, but however, although we get a non-adaptive construction, this parameter still looks far from satisfactory. So we ask, what does the right construction should look like? So this can be answered by looking into another primitive, which is a pseudo-random generator. Because the construction of pseudo-random generator and the WOOFs from one-way function are very similar. I will demonstrate this similarity with the case of regular one-way functions. So one-way function is regular if every image has the same number of pre-images. So a result in 22 by Melson and Zhang was also the author of this paper. They give the following construction. So let's take n independent input x1 through xn, and we pair x1 with fx2, x2 with fx3, and all the way down to xn minus 1 and fxn. And we hash some bits out of each pair. So here h is some simple hash function. So note that each pair has real entropy exactly n, given other parts of the output. So if we hash out more bits, the output should be longer than input, so we get a PRG. On the other hand, if we hash out fewer bits, the output is shorter than the input, we get a shrinking function, and we can prove that this is a collision resistant, this G prime. And one thing is that in the PRG construction, we drop the unpaired fx1 and xn. They are unpaired, so we drop them. While in the hash function, in the latter one, we output fx1 and xn. But since we hash fewer bits on each pair, we still get a shrinking function. So we can prove G prime is collision resistant on random inputs, then it can be easily turned into a WOOF. So it is very surprising that there is no efficiency gap between PRG and universal one hash function if the one-way function is regular. Moreover, these constructions are somewhat tight because there is a matching lower bound by Holenstein and Senha. They prove both for PRG and the WOOF. So the number of calls are tight in the case of regular one-way function. So this gap between PRG and Wolf in the arbitrary one-way function case is quite surprising. So in order to close in this gap, we introduce another construction which is very, very similar to the HRV PRG construction. This PRG construction is the state-of-the-art PRG construction for a one-way function. But we cannot prove that this construction is Wolf. So we prove that it is an almost Wolf, which is a relaxation, I will introduce later. So let's get into more details about the constructions. So in order to demonstrate our Wolf construction, I would like to introduce a framework called computational entropy. This framework is for constructing primitives from especially arbitrary one-way functions. So starting with an arbitrary one-way function f, we first construct another function g, which is called computational entropy generator. And by manipulating entropy and do some extraction step, we get primitives like PRG, Wolf, etc. So this looks abstract. Let's take PRG, the HRV PRG construction as a concrete example. So in their construction, they first build some function g, which has next bit pseudo-entropy. This means if we denote z, the random variable gx by z, where x is a uniform random input. So z is computationally indistinguishable from some other variable y in a bitwise manner, and moreover, y has more entropy than z. So you can see in this this expectation is taken on a random index. If you replace the yi by zi, you will get exactly entropy of z over L. But we have entropy of z over L plus delta. This means on average, each bit exhibits some extra delta pseudo-entropy. So next, we want to extract this turn this kind of pseudo-entropy into pseudo-random bits, then we'll get a PRG. So this is the HRV PRG construction proceed in 4 steps. So the first step is repetition, meaning that we take many independent copies of this G and arrange like a matrix. There are Q rows and T copies in each row. Since each G has L bit long, we have in total T times L colons. And the second step is add a random shift to each colon. So this aims to average the colons because after this random shift, when you look at one colon, the indexes in this colon in each small block is uniformly distributed from 1 to L. So this corresponds to the second bullet here. You can see we have roughly each colon has more pseudo entropy than its real entropy. Then we can use some extractor to extract the pseudo entropy, get more pseudo random bits than input. Before that, there are a little bit detail because you can see in the picture on the rightmost side and leftmost there are some colons. They are unfilled, so we just simply drop these colons and hash some bits out of each colon, then we get a PRG. This is HRV construction. So previous Wolf constructions also fit into this framework. They define something called inaccessible entropy. So it is natural to consider whether we can define some next bit version of this inaccessible entropy, and the right construction in our mind is something similar to the HRV PRG construction. So more precisely, it's very similar to the regular function constructions from regular one-way function. We consider if we, instead of dropping these unpopulated colons, we simply output them. And for each colon, we have fewer bits. So this is very similar to the regular constructions from regular one-way functions. So we might think this could be a Wolf. But we cannot prove it. We introduce something called next bit unreachable entropy and show that this is an almost Wolf. Yeah, there is a little bit gap here. So I will introduce the two notions in order. So the first one is next bit unreachable entropy. Means that if we say this function g has next bit unreachable entropy delta, if for every index we have some inputs such that it is hard to flip the ith bit while staying inside the UI. Here, x is a random input, I is a random index, and x prime is the output of the inverter, the adversary. So this says looks a little bit hard, but it basically says the adversary cannot manipulate the ith bit of x of gx. So the second item says the unmanipulatable bits are abound. So U is large, meaning that we have more unmanipulatable bits than it should have information theoretically. So to see this, because the entropy of Gx is at most m, because the input length is m, and we have L bit output, so there should be L minus m bits that the adversary cannot manipulate, cannot flip this bit while fixing the prefix. So, but we have a delta more unmanipulatable bits. This is where where we get our advantage. So the third item is quite technical, so I will not get into that. But our idea is that we can use a very similar generator and prove that they satisfy all the three conditions. So our next bit unreachable generator is very similar to the HRV next bit pseudo entropy generator. So in their pseudo entropy generator, they output fx and hash of x by some hash function. And in our construction, we just add a more hash to f. We also hash f. So they are quite similar. So, after using this next bit unreachable entropy notion, we can prove that this construction is indeed an almost woof. So what is an almost woof? It means that there is a negligible fraction of inputs, which are bad inputs, such that the adversary actually can find collision x prime, but only from this small set. This looks weird at first glance because anyway, the adversary can find a collision, although it's in this small set. But we have the following justification because we notice that the HRV PRG construction is actually an almost PRG. So they actually prove that there is also a small set B such that conditioned on the input seed is not in this B. The output of their construction, G, is computationally indistinguishable from uniform bits. But as you can see, the computational indistinguishability is quite robust. You can just remove this condition U not in B because B is very small. It's still this statistical distance is still very small. It's increased by a negligible amount. So this does not affect anything. So fortunately, almost PRG is trivially a PRG. So, but this is clearly not the case for woof because if we have a small set of bad inputs and the adversary can find a collision. This is somehow somewhat worst case manner. Interestingly, our non-adaptive woof construction can be derived from the almost construction, almost woof construction by simple modifications. So in order to turn this into a woof, we just use large QNT, meaning that we have more copies. Of course, this is less efficient. And instead of hashing a single colon each time, we hash a block, a L time Q block. And we can prove that the construction is collision resistant on random inputs. And then we get a woof by the standard transformation. So finally, we give some open questions. First one, of course, we conjecture that our almost woof construction is a full-fledged universal hash function. So maybe we need to modify our next bit unreachable entropy definition to give a more exact characterization. Yeah, and the second thing is that maybe a more natural computational entropy generator can be used. For example, here Gx is just fx and x. So because this generator is used by VZ12 to construct a PRG. Another direction is to prove lower bounds on black box constructions from one-way function, both on the seed length and the number of cores, and both for PRG and the wolves. This is already done for regular one-way function case, but in the case of arbitrary one-way function, there is no matching lower bound. Yeah, thank you, and I'm happy to take questions.
Questions from the audience? Okay, then I have a question. So this is one way on random inputs, right?
What?
The results you're presenting are one way on random inputs, or you're working with random inputs, right?
No, there is you can simply turn that collision resistance on random inputs to a wolf, standard transformation.
What happens if the inputs are not entirely random? They share a few bits, but are different in other bits.
I think this is, if you can still use the transformation, but maybe it would not be a wolf, I think.
Okay. Okay. So if there are no more questions, let's thank the speaker again.
Okay, thank you.
So the speaker for the third session, okay. So the next talk is, XOCB, Beyond Birthday Bound Secure Authenticated Encryption Mode with Rate 1 computation. And the speaker did not come to speak to me before, so I will ask the speaker to present himself and the co-authors because I don't want to get the names wrong.
Hello, this is Seonghwa Hwang, and I will introduce about our paper, XOCB, Beyond Birthday Bound Secure Authenticated Encryption Mode with Rate 1 computation. This is a joint work with Zhenjian Bao, Akiko Inoue, Byung-hang Lee, Juyong Lee, and Kazuhiko Minemach. Before we start, we give an overview of this paper. We present XOCB, a new block cipher mode of operation for non-spaced authenticated encryption. XOCB has the following features. First, it mostly follows the structure of OCB. Second, it has beyond birthday bound security. And third, it is parallelizable with rate 1 computation. First, I will introduce about the OCB. OCB was first proposed in CCS 2001. OCB mode is the most widely used seminar scheme due to its efficiency and the security. The main point of OCB is adding the random masking value to the input and the output of the block cipher. Why these random values are important? Because of the collision. Collision means that there are same values to the input of the block cipher in different blocks. And this makes the adversary to easily do the distinction attack, so collisions should be prevented. To do that, the masking should be distinct and generated from the reasonable scheme. And this OCB has the birthday bound security. However, the computational power and the amount of data have been increased recently. In particular, exabyte 10 to the 18 byte data is already in use, and zettabyte 10 to the 21 byte data is in near future. In this case, just birthday bound security might not be enough. Therefore, a higher level of security is desirable, called beyond birthday bound security. Then how can we improve the security? Here is an example. This is XORP, a pseudo-random function. If we give a message, the message is concatenated with 0 and 1, and each of them are fed to the permutation. And the result is XOR of 2 outputs, and XORP is a secure pseudo-random function up to O2 to the n queries. If we use this construction, it might be possible to make encryption mode having beyond birthday bound security. And one of them is CENC. CNC uses nonce and increasing it one by one, and each of them are fed to the input of the block cipher. And the output of the first block is added to the other output, and these values are used as the key stream of the message. Since there are no collision between two blocks in one encryption, and the key streams can be seen as XOR of two outputs of the block cipher, so CNC has the beyond birth bound security. However, CNC itself is not authenticated encryption. The main reason that CNC cannot be authenticated encryption is the messages are not fed to the input of the block cipher. So it cannot authenticate based on the security of block cipher. So CNC uses hash-based MAC to authenticate. Then, to obtain a authenticated encryption having beyond birth bound security, we have design principles as follows. First is XORing two outputs of the block cipher, and second is the message should be fed to the input of the block cipher. By these design principles, we designed XOCB as follows. It is similar to OCB, but there is one additional layer, one additional XOR layer, and this value is generated from the first block with encrypting 0, and this value is added to every message encryption block, so all the ciphertext can be seen XOR of two outputs of the block ciphers. But there is so we can expect XOCB has beyond birth bound security. But there is one problem. Unlike CNC, there might be some collisions between two blocks. And as I said, it is very critical to the security. So it is important that the adversary is hard to make collision between two blocks. So the maskings should be carefully constructed. To do that, we generated masks as follows. First, using CNC star, we generated 3 random values. Using these 3 random values, we constructed each masking as follows. Using this masking scheme, we can leave at least one random value between any two blocks, so we can avoid a collision. Now we give a proof sketch. We used H coefficient technique. For the probability to get a good transcript in the ideal world, we use extended mirror theory twice. The first is for the evaluations in the mask generations and message encryptions, and second is for evaluations in the tag generations. So what is H coefficient technique? H coefficient technique is a special technique that upper bounds the adversarial distinguishing advantage between a real construction and its ideal counterpart. After the adversary finishes the queries, the adversary gets a transcript, which consists of all the information the adversary has obtained during the attack. In our proof, the oracle also gives the evaluations determined in the query phase. In the real world, the oracle gives the real evaluations, and in the ideal world, the oracle gives the evaluations by a certain process. Then we can divide the set of all possible transcripts into 2 subsets, good transcript and the other is bad transcript. If there exist non-negative numbers epsilon1 and epsilon2 satisfy these conditions, then we can bound the distinguishing advantage. In our proof, the important part is bounding the probability to get good transcripts in the ideal world. To do that, we use mirror theory. Mirror theory is a very powerful tool to estimate the number of solutions to a certain type of system of equations. Look at this picture. This is similar to XRP, and there are 2 inputs, AI and BI, and there are 2 unknown values, xi and yi, which is the output of the block cipher. So we can induce the equation that xi XOR yi equals zi. And we correct these equations by applying mirror theory. We can estimate the number of solutions to it. However, in the decryption queries, there might be both, which means no information. So in this case, we should also include the non-equations as well as equations. This is extended mirror theory, and we used for the truth. Yeah, so in our proof, the XOCB construction can be seen as the XOR of two outputs, and each ciphertext can induce the equation x0 XOR x1 equals c1 XOR delta 1 XOR delta 2. And we can collect those equations for all the ciphertext blocks. Then the probability that those evaluations are determined is the inverse of the number of the solutions. For the detailed proof, please check the full version over the paper. As a result, XOCB has the following security. Q is total number of queries, and sigma is total number of queried blocks of n bits, and L is maximum query length in n bit blocks. And the lead term is colored as the red color, and by this lead term, we can conclude that XOCB has beyond birthday bound security when L is smaller than 2 to the n over 2, and has 2n over 3 bit security when maximum query length is constant. This might not be a practical problem in real-world applications, since many practical communication protocols specify a maximum packet length called MTU. And here is a comparison table with other schemes. You can check that XOCB has good advantage in rate and security. We also implemented XOCB in two platforms. The performance of XOCB is quite close to OCB and faster than CIP for 6x64 platforms with AES-NI. And for 8-bit AVR, the initialization cost is not negligible and affects the total performance. So in conclusion, XOCB is a new authenticated encryption mode which mostly follows the structure of OCB. It has a quantitatively stronger security than the seminal OCB while inheriting most of the efficiency advantages. We can also consider further research topics as optimizing the scheme to reduce computational overhead, reducing the length contribution to the bound, or more comprehensive benchmarks. Thank you for the listening.
Thank you for the talk. Any questions from the audience? Okay, then let's thank the speaker, all the speakers of the session and the speakers of the day, and I'll let them know that we thanked them. So.